So next we're going to be talking about minimum spanning trees. So before I can get into that, I got to tell you what a minimum spanning tree is. And then we're going to start talking about properties that minimum spanning trees have. And also, in addition to this, how exactly we compute a minimum spanning tree, or at least one way to do it. So a couple of things. So first, as a reminder, we need to know what a spanning tree is. So you might ask, Dan, what exactly is that? So suppose I give you a graph. Just let's keep it very simple here for our discussion here. One, two, three, four, like this. So this is a graph G, and I can compute a subgraph of this given graph G. What's a subgraph? It is just a subset of the vertices and edges such that it forms a graph. So for example, I can take 1 and 3 here. Sorry, I'm getting very excited here. 1 and 3. I can also include this edge here, and that forms a graph. So I can't have like a dangling edge where it doesn't have one of its endpoints, right? That makes no sense. That's not a graph. Because it would have to include the opposing endpoint. So likewise, I can also take 1, 2, and 3, include all 3 of these edges. I can also include only these 2 edges. Those will all be examples of subgraphs. So a very natural question is, okay, is there any nice way of building one of these subgraphs such as nice properties? So what we call a spanning subgraph is just simply, I pick off a subgraph. Say, maybe I pick all 4 of these vertices. And say I take, I don't know, say maybe this triangle here, and maybe that single edge like that. Notice that this subgraph contains all of the vertices in the graph. But that means it's very special in the sense that it has all the vertices. And it also is a subgraph, so it consists of a subset of the vertices and edges. So that's why we have both of those 2 things. So that's what we call a spanning subgraph. But maybe we want to have a much better structure than just this. So that brings me to talk about what a spanning tree is. So what is a spanning tree? It is so spanning simply means it contains all the vertices of your graph. It is a subgraph, a spanning subgraph. So, but it's not just that. The reason why we call it a spanning tree is that it has to be a tree, right? So as soon as I spell it out like that, it's like, oh, that's a piece of cake. So just as an example here. So the edges I'm just highlighting here, those 3 edges with those 4 vertices is an example of a spanning tree. Notice that it has all the vertices in the graph. It is a subgraph. That means that it is a spanning subgraph, but it has no cycles. And it's connected, right? So that means it's a tree. If it wasn't connected, it would be what we call a spanning forest. Which makes sense given the fact that it has no cycles in it, but it's not connected. That would mean that there's a collection of spanning trees. But each one's spanning amongst the vertices that are in its connected component. So I just feel like I need to acknowledge that. So we have this concept of a spanning tree. We've talked in previous lessons how we can compute a spanning tree. For example, you can use DFS or BFS, so depth first search or breadth first search. You can use these to compute one of these structures. So you can use any of these 2 graph traversal algorithms in the way that we've discussed previously to compute a spanning tree. But here's the thing. Here's the kicker. I would like to find not just any spanning tree. Suppose that I assign weights or costs to these edges. So suppose it's like a 5, that's 1. This is a 1. This is, I don't know, that's a 5. Now let's make this a 1. Makes it extra fun. Got a 1, and let's make this one a 5. So now I have a weighted graph over there. I've assigned weights to all the edges. And then I want to ask a very simple question. Like, how can I compute a spanning tree such that if I add up the edge weights of the edges that it consists are part of my spanning tree, such that the cost of these is as small as possible. So just as an example, this spanning tree I have computed here, the total cost of this tree would be just simply the sum of all of its edges. So it's 5 plus 1 plus 5, which that is 11 if I've checked correctly. But however, that isn't the optimal answer. That isn't the optimal answer. I could instead pick this instead. Notice this right here is actually the true minimum spanning tree. Notice that the cost of this spanning tree is 1 plus 1 plus 1, which is 3. Much, much smaller in terms of cost. And you might say, Dan, why should I care about any of this? Well, let's put it in some real world kind of terms. Okay, so you imagine you have this graph here. And you're like, hey, Dan, suppose that I am some guy. I'm going to manifest this in a few different ways so it's a little easier for you to see what's going on here. Suppose I'm some planner, and I have a network of bridges I want to build such that I have some lovely, lovely friends on my islands. There's potential places where I can build bridges for a network of islands. And each island may potentially have a turkey on it. Now maybe you're some aficionado and you're like, I got little turkeys. Got my gobbler on there. Got the badunkadunk, okay? So suppose that my islands have turkeys on them, and I want to have some way of building bridges so that the turkeys, because these are really lazy turkeys. See, turkeys can fly, but these are really lazy turkeys, okay? They're on a tropical trip. They don't want to go anywhere else but walk, okay? They just want to go stroll around. I want to be able to build a network of bridges so that the turkeys, suppose that the turkeys here, could be here, could be here, can travel from any one of the islands to another island. But I want to, because I'm really cheap. And my really lazy turkey friends really don't want to have to, they don't really care as long as they get to where they want to be. But I want to be very prudent with my money, okay? These bridges cost money to build. And suppose that it's just like that one over there. Suppose that, like I said, I am building a bridge, and each one of these ones here, that's $500 to build this bridge. It's $500 to build this bridge. Perhaps there's some rocks or something, some pointy, jagged rocks to make it a little bit harder for the workers to get to those bridges. Well, not those bridges, but the water around there to build some of those pegs into the ground. And say these ones only cost $100. So you might naturally ask, how can I build the network of bridges such that my lazy turkeys, which I must stress, they don't have to be lazy turkeys, they could be tourists, which I must stress are not lazy turkeys, everybody. Don't call your favorite friends coming to visit you lazy turkeys, just don't do it. They will not want to come again. So that my lazy turkey friends can go from one island to another, but notice that this is considerably cheaper if I just build the bridge here, here, and here, instead of building, say, any one of those $500 bridges. So notice I'm not making any claims about how fast my turkey friends can take from one bridge to another. It's just the fact that they exist. so that the turkey can get to any one of the islands, but I'm minimizing the cost to build all of my bridges. Now you might say, Dan, this is a rather cute example, but what exactly does this mean for like real world settings? Okay, instead of thinking of this as just a bunch of islands, suppose I have a bunch of power towers. Suppose I have like, instead of thinking of these cute islands like, here's my, so suppose I have some power delivery that needs to go from a tower to another tower. I don't claim these to be beautifully drawn generators or towers, okay? But the point stands is that you're going to end up with some towers that you need to deliver energy to customers. And you have potential to build lines from the towers. So you can see why this isn't just a lazy turkey island problem. This is actually an infrastructure problem. So in this case, instead of a building like this, you can just imagine just like if I was building this line, that line, and this line, this would be much cheaper for me to build the towers like this. You can also imagine this in all sorts of other ways. You can actually imagine these as computers too. Like you can imagine a computer network and you want to think about transmission between computers and the cost for which to build those lines, or the cost for maintaining those lines. You can formulate these in many different ways. That's the point I'm getting at. These are network design problems. That's the big point I'm getting at. This is a very elementary network design problem. Whether it be lazy turkeys with islands, transmission of electricity, such that you build the towers for the cheapest cost. The point, of course, is, remember, it's about the building of these. We're not making claims about them being the shortest route for the lazy turkey or the shortest route for power delivery. That's not a claim we're talking about here. We're just talking about the infrastructure, building it. Okay? So I'm hoping that this emphasizes why just studying, say, this concept might be enough for you to think about this a little bit more delicately. And I encourage you to think about ways that you might consider a network design problem like this and add more constraints to it. So we're going to focus on just computing a spanning tree of minimum cost, and that gets me to talking about what a minimum spanning tree is. So I must stress that there's many reasons why some of these phenomena take the form of trees. I just give you one reason, okay? It's that physical costs maintain that it's easier to control. Then also you get all these properties that we talked about with graphs. For example, the unique paths that exist. So if, say, one tower goes out, you don't have to worry about, like, you know that for sure that there's some route that you know exactly where the point of error actually occurred. Either way, these are things I want you to think about. Sorry, I'm just getting really excited when I bring up these things. But like I said, I don't claim that this is the perfect way to design a network. I just claim that this is an elementary way of thinking about minimizing costs for building a network. Okay, so given a connected weighted graph, G is equal to VE. What I would like to do is I would like to compute what is called a spanning tree. So it's a spanning tree. So remember, a spanning tree is a spanning subgraph. So I'm computing some subgraph that spans the vertices. A spanning tree T, whose total cost, and remember the cost of the tree is simply the sum of all of the weights on the edges in the tree. So that's what this means. I take each edge in the tree T, so that means in, and I sum up all of their weights. So I say this is smallest possible. So we're going to be considering what we call a minimization problem. So that brings me to talk about what the minimum spanning tree problem is. So we abbreviate minimum spanning tree as MST for the sake of brevity here. And the MST problem is really quite simple once you understand what a minimum spanning tree is. We have one right over here. The red edges is an example of a minimum spanning tree. I've also included another example in the notes. It's a little bit bigger. So if you're given a connected weighted graph, and I must stress that when I say weighted graph, I'm talking about an undirected simple graph, but I'll have more discussion about that simple aspect eventually. Weighted graph, G is equal to VE. Sorry, it's getting cut off a little bit. What we're going to do is it's about compute. You have to compute a minimum spanning tree T of G. That's all it is. That's what the minimum spanning tree problem is. That's what the minimum spanning tree problem is. So that's the one we're going to be seeking to solve here. So this is an example of what we call an optimization problem, which I want to dedicate a little bit of time to discuss right now. So let's talk a little bit about what an optimization problem is. So I want you to think right now of what, like you've probably heard of the phrase optimization before, and you might be thinking, Dan, what do you mean by this? Now, I usually talk about computational problems in a very simple way, but an optimization problem can be seen as a generalization on top of that. So in fact, it is. So just to give you some flavor of what I'm talking about, just to kind of remind you what a computational problem usually is defined like, then I'll sort of add on top of it kind of the lingo that we need to talk about this. So a problem consists of problem instances, right? So if I have my problem, so it has a bunch of instances. So suppose it's problem pi, so its name is pi. And inside of here are all my instances. All of these are instances of my problem. And each one has a solution. So each one has a solution, or if it doesn't, then some problem formulation will have it where you know what that means, right? So that example, it would not have an answer. But my point is that there's problem instances, each has a solution, and when you design the algorithm, you pick off any one of these dots, and then you feed it to the algorithm. So you take that input, produces output. If the output matches the solution, you're done. But it has to be that every one of these dots, no matter which one it is, and keep in mind there might be infinitely many of these. Usually that's where the case is. There's an infinite number of them. That's usually when a problem is a little bit more interesting. If it was just some finite number, you can just exhaust all of them. It might not be practical for all cases, but most certainly that's what delineates between an interesting problem and one that might be a little easier. My point is that each one of these, you feed it to the algorithm, take each one of these dots, which is the input for that problem instance. If you can get the correct output, the solution every time, we would say that algorithm is correct. And if you could do it for every one of the dots, we say the algorithm correctly solves the problem, right? That's how we mean when we say we've solved a problem in the context of algorithm. So let me give you kind of like the version of this when you take an optimization problem. So if we have an optimization problem pi, so in here, again, you're still going to have instances. You're going to see that's very much a generalization of the same idea. So you're going to have instances, just like we had before. So there's instances here. No different. So this is problem pi. Has all these instances. Nothing has changed yet. The thing that differs now, instead of just having a solution, each one of these has a set of feasible solutions. So you might ask, Dan, what's a feasible solution? It's simply a solution, as the name suggests, that satisfies all the constraints of your problem. So in our example, the minimum spanning tree problem, it has to be that whenever you spit out an answer to me, it has to be, one, it's a spanning subgraph, and it's also a tree, right? It has to be both of those things, a spanning tree. So any spanning tree in that example would be a feasible solution. Why? Because when you frame it like this, like no matter if you gave me the black spanning tree or the red one. It doesn't matter, it's a spanning tree. So in our example we had over there, an example of a feasible solution would be a spanning tree. And for every one of our optimization problems, we'll have at least one goal. So we'll have some goal. So usually it is that you minimize or you maximize. So in our case, are we minimizing or maximizing? No, we're not. We're not maximizing, although you can rephrase this as a maximization problem over there. But we're going to talk about this as a minimization problem. So you might say, Dan, what are we exactly minimizing? Well, how did we measure the cost of our spanning tree? Well, we had the function, our total cost was, so we have what we call our objective function. So that's the other ingredient to this, is the objective function. So we have instances. Each instance has a set of feasible solutions. These are defined by the constraints of the problem. And then what happens is you have an objective function. The objective function is how you measure how good an answer is. Okay? So in our example, so this is how you measure quality of a feasible solution. And now that I have a goal in mind, based on this objective function, I can toggle whether it's minimizing or maximizing. In this case, I'm going to imagine I'm pressing this button here. I'm going to press it's minimizing. So in this case, my goal is to minimize the total cost of the spanning tree. So any answer that has a spanning tree, that's a feasible solution, but we want these special kinds of problems, solutions. So there's a specific set of them. Now, I don't know how many there are of it. Depends on the problem instance. Like I said, each one of these is defined by the problem instance. There's going to be some of these called optimal solutions. So you might ask, Dan, what exactly is that? All it is where when you measure this, the objective function, it's exactly equal to the value of the optimal answer for that instance. So in our case, as we said over here, this is when you compute you get a spanning tree whose total cost is as small as possible. The smallest possible cost is the optimal value, the optimum. So when we put this all together now, if we frame this, our minimum spanning tree problem in this context, this is actually what an optimization problem is. Notice it's just a generalization of this concept. So it's one way of generalizing it. So now let's look at this. So if I have the minimum spanning tree problem, I just want to kind of introduce you to this so you get some familiarity with it, because when you encounter more and more optimization problems, thinking about it more as I have a bunch of constraints, I have something I'm measuring about how good the answer is, and what is my goal with that measurement? Am I trying to maximize, minimize? Am I maximizing something that with such that there's a minimum? This is going to be rather relevant when we talk about optimization. But the point is that we want to compute these ones that are optimal solutions for every one of the instances. We would say that an optimization problem is being solved by an algorithm correctly if every single time it spits out an answer, it's one of these ones, the optimal solutions. That's what normally people say when they say they've solved an optimization problem. Exactly. Yes. So let's put this in the terms over here, because I feel like I want to do this, put this all together for you. So that way, when you walk out of this, it's not just learning about what this is, but you also get a flavor for what an optimization problem is. So you can lay this out more formally, but I just wanted to give you a flavor for this. So you already know what the instances look like, right? We defined that over here. Nothing special. It's just you're given a connected weighted graph. That's the input. That's what each instance is defined by. And then you have a feasible solution. So what we require is a spanning tree. And you might say, okay, Dan, what's the objective function? Well, it's just the sum of all the weights, right? So I'll call that spanning tree T. I want to minimize this, so I'll have a goal. Is the minimize. So this is how I can put the minimum spanning tree problem into this framework of an optimization problem. So hopefully that's pretty interesting stuff, right?